welcome. So last time we started sequential logic. So we talked about each device, or for sequential logic, we are looking at moving from states. So we went in the finite state machine, which was a state. So we looked at the digital lock. So with the digital lock combination, you had to press certain sequence of numbers. You noticed in there that for a sequence of 4, you had to have 5 different states, right? Because you had to have, before you even start, what number did you press first? The second number needed to be, the first number needed to be correct, then you went on to the second number, then the third number, then the fourth number. Once you got to that place, then you were able to open the lock. So a finite state machine needs as many flip-flops as states that you have. So to code in 4 states, you can start at 0, so you can count that one. So it was 0, state 1, state 2, and state 3. So you needed to have how many flip-flops to do a number 4, 1, 2, 3, 4, which would be 0, 1, 2, 3. So you needed 3 flip-flops to code 0, 1, 2, and 3. So 3 flip-flops were in that one, and they were your memory elements to differentiate between combinational logic, which just was a very straightforward, if I have 0 and 1 as my input, then I get this out. If I have 1, 1, this output, so on. So those are not having a memory element. So the difference between the sequential and the combinational is that memory element. So with that, we talked also about asynchronous and synchronous. Do you guys remember what asynchronous means? It means what?
Without time.
Okay, so without time meaning that you have an event happen and then it moves right to the next event. So that event is what is triggering the next one. So it's not clocked would be another way you could think about that. So synchronous meaning that you have something that's synchronized. So thinking about it that way is with a clock. So you're going to need a clock with a synchronous. And then everything happens on a clock in a synchronous system. So those are some of the learning objectives that we went over last time was synchronous, asynchronous. Go backwards. What else did we go over? Oh, and then we looked at the 7-segment display, which is a common device used in digital logic. And we talked about memory elements, which can be 3 different things, a latch, a flip-flop, and a register. And then we talked about that sequential logic and so the system we went through, I'm going to call it a finite state machine. So we talked about the design process, which was also the design process. We had that state diagram. So remember, this was your state diagram. So this is defining how many states you need within the system. And then we looked at the state table. And the table is what's going to help us determine the logic needed. And with that, you need to understand how to create the logic from this using that sum of products. So we created the expressions, and then from the expressions, you can create that digital logic. Okay, yes, question.
Why is the C1 wire going in after the flip-flop? Is it connecting an OR or?
So that's because, and that's what differentiates a combinational to the sequential, is we have a current state and a next state. So visually, it's easier to see in this where you have, if you're at the current state of 0 and you press a 1, then you moved into this next state. And then so on to the next state. When we code the actual table, we used a binary representation for the states. And the binary representation then starts to take the input as that current state. And depending on your current state, the output is your next state. And so we use logic to get from the current state to the next state, and then the flip-flop moves us from, so this is your current state, and it will get fed back into the system for the digital logic, which was here.
Oh, okay, I see.
And then that next state now then becomes the current state. Does that make sense?
Yeah,
So it's that, yes, it's a current state until the next clock, and then that next state becomes the current state. So that's how that flip-flop works in there for that memory element. So the digital logic creates the next state, but then the flip-flop will actually retain the next state and replace the current state with the next state. Does that make more sense? Okay. And yes, that can be a little confusing at first. All right, other questions? Any other questions? Okay. So today we'll kind of go over some questions that you could expect for things like this. I guess briefly, like here, I could say for this type of a system, how many states would you need? And to clarify what those states would be. So in this one, you would need 3 states if you had 0 in there, which was really 4 states. So you would say you would have 4 states, and then you would need 3 flip-flops to encode that many different states. Does that make sense? So that could be a question that I could ask. I could give you a table like this and ask you to derive the Boolean expressions and or the Boolean or the actual digital logic for each of those. Yes.
So depending on how many states there are, you need like the number of states minus 1 flip-flops?
So in this case, if I had, I have 3 digits to define those states, so I need 3 flip-flops in there. Yeah. All right, other questions? Okay. Okay, so that kind of summarizes what you needed to take away from that. The only other elements that we haven't gotten to yet are some, are called, so another common ones are shift registers, which we didn't get to last time. And then another component that's very useful is a counter. So we last time also looked at the clock and how to create a clock from that 555 timer chip. And then we also looked at the 555 timer that it can actually create what's called a one-shot trigger, and it will create a pulse length depending on that capacitor value. So it would create it to be a specific length of time. So that's what the 555 timer is used for, is either a clock or it can be used to create a time period with a very specific time on it. So it would give you like a high until that time is ended, then it would go low. So it's great to keep track of a time. So the other ones, again, shift registers, and then we're going to look at counters. So these 2 device components are also very common. The other part of today is then we're going to simulate the shift register and the counter, and then we're going to go through some practice problems similar to kind of other ones you could expect to see next week. So that reminds me, exam is next Monday. So exam 3. And then the optional final will be next Wednesday during class time. So you'll have 80 minutes to retake any of the 3 exams that you want, or all 3 if you want to try and do that. It's very difficult in 80 minutes, but if you know it really well, some of you got done with some of the exams in like 20 minutes, so I guess it is possible. Final project will be due next, so not this Friday, but a week from Friday. So you have 2 weeks. Friday, October, is it 3rd? 3rd, yeah, October 3rd. And so for that, you will be demonstrating in class in small little groups. We're going to break up into groups, and the TAs are going to help grade each of you. It will be a simulation, and I will be writing up more of the requirements for that by tomorrow. So I'll say by the end of today, but by tomorrow, that final project requirement will be specified. You can do any of the simulations we've already worked on and just expand it a little bit to include. It will pretty much be something that you need to simulate a model for something you're measuring from the environment. So it could be what you've done in lab if you want to use that instead, or something new. In the stock room, which is kind of fun, on the wall as you walk in there, they now have a nice little display with a whole bunch of different types of sensors in there or output devices in there, so you can kind of go and browse those if you want to. There's like a strain gauge I noticed, and some other sensors that are in there too, and some different motors. So you need it to do something that will show an input measurement, so you can model what your input would be, whether it's, for example, the light sensor photoresistor. You measured in lab some of the values for that at different conditions, so you could use that as your input. You would model it based on what your measurements were, and then have it do whatever you want it to do throughout the circuit, and then you would just need something that outputs. So a light is an easy output. You have a motor also from your kit, and if you want to use any other ones, you're welcome to use that. So it just needs to be a simulation of those. For the final project in 1235, you'll need to add on a time element to it, so an RC or RL or RCL, if you want to get that far, components in it for the final project in there, and then you'll build it along with the simulation. So in this part, you're going to do the simulation, and then in the lab portion, you'll finish out a final project building it in there. So if you want to think of something, and you can do the same one, or you can change it by the end of the semester for that one. Okay, any questions about what's coming up? So the exam will be in the same Engman Lab, same format as we've had. It will just be on this other content. So Engman Lab. All right. So the shift register, I kind of mentioned last week, it's a combination of those flip-flops. So each one of these is a D-type register, or D flip-flop, and so this is how many D flip-flops in there? It's 4, correct. So it has 4 D flip-flops in it. It comes as a chip, and the one you have in your kit is actually 8 of them. You don't have like 8 LED lights, so in the lab you're going to actually build this with just 4 of the, you're only going to use 4 of the lines out of it. So the shift register will take in data, and then it will output data. So as you put it in, it will store it, and then you can basically read the data all at once if it's parallel output, or in series out. So you have different combinations that you can have. So one is to have serial data input and serial data output. It's a little hard to read probably. Yeah, that's better. Another one is serial data in, and then you can read it all at once as a parallel output. Yes.
Is this what the CPU registers are?
So on a CPU, you mean? Yeah, yeah. So they're registers. So depending on, yeah, but same thing, same idea. Yep. So they store data, and then you can retrieve data from them. So the last way this can happen, well, no, I guess there's 2 more. So you can have data in all at once. So you would put those in parallel, and then you could read them out in series. Or you can put them in parallel and read them out in parallel. So this is serial in, serial out, serial in, parallel out, parallel in, serial out, parallel in, parallel out. So that's what all of those acronyms are for. So what this means is just different ways of putting the data in, getting the data out. All right, so as you're doing each one, this is going to be clocked. So what kind of a device is this one? This would be asynchronous. Because it is clocked. So this is kind of showing each of those in more detail. So this one, your serial data goes in here, and then you're going to read this once everything in. So as the data comes in, it comes in here. First clock signal, it will be on this wire here. Second clock signal, it will then have moved to here, and what was on this one then moves to this one at that time period. So you can see how it shifts it, and that's where it gets its name of shift register. Third clock cycle, it would be here, and fourth clock cycle, it would be there. So how many clock cycles do you need to be able to read accurately what this is? Correct, you would need 4. Okay, so you can see here, first clock cycle, your 1 is here. Then if you have a 0, so at clock cycle 1, you have a 1 go in, and then everything else is going to be a 0 after that. So the 0 becomes here, 1 is there, then 0, 0, and then the 1, and then 0, 0, 0, 1. And then I'm going to read it at the 4th clock cycle. So I have to be very careful with my timing to know when is that data actually accurate. So this would be the accurate one at clock cycle 4. Does that make sense? Okay.
Can you explain that one more time? Why it's accurate, more accurate than the position?
So at the first clock cycle, say I have a 1, like I have a high value sitting here at the first clock cycle. So the clock cycle goes on, and that 1 moves here. But these do not, these are kind of like, they probably have 1 or 0 on them, but I don't know what that means. So I've timed it so that I know right when I put in the first bit of data, what timing that is. And then I then change this before the clock changes to a 0. And when the clock changes, that 1 moves from here to here, and the 0 is put into that one. And then and then I keep a 0 on that input, and the next time this is then going to move here, and that changes to a 0 and a 0. And then by the 4th clock cycle, that changes to a 0, 0, 1. So I know then that I'm reading out the correct number. This will be what's called the most significant bit. And so I would actually read this as 1000. So what decimal number is this? Hearing differing ones. So remember, this is 0, 1, 2, 3. So it's what? 8. So that's the decimal number 8. Okay. All right. All right, serial in to serial out. Data comes in serial, and then it's read out as serial. How many clock cycles before I'm going to get all of the information? Okay, so first clock cycle, go through this. Say I put a 1 on there, and these had some data, but I don't really know exactly what they are because I haven't timed it correctly. So at time 1, I say, okay, I'm going to shift in the first one of what I know. So this goes into a 1. That's 1 clock cycle. Second clock cycle, it gets shifted here. And then say I change that. Third clock cycle, that first bit goes here. Fourth clock cycle, it goes here. But now everything else after it has to keep coming. So fifth clock cycle, I have that 1. Go backwards. Okay, say I'm putting in 1 0 1 0. Let me go back. Okay, so first clock cycle, I put in a 1, I clock it, and the 1 moves here. Change that to a 0. This gets moved here, and the 0 moves in here. Then I change it to a 1. This shifts here. This changes to a 0. This changes to a 1. And then I have a 0. This shifts here for a 1. The 0 moves here, 1 moves here, and 0 moves here. So I have in the registers now, after 4 clock cycles, all the right numbers, but now I need to read them out. So 4 cycles to get the data in. And then I can read out. On the 4th one, I read the first one, which is 1. The next clock cycle, which will be 5, I'll read the 0. Next one, I'll read 6, will be this one, and then a 1 for 7. So I'll need 7 clock cycles. So that will take a little bit more time to read in the data and read out the data. So serial typically is longer. Any questions on how that kind of works? Yes.
So that last cycle, it puts 1 in on the front, and then it puts a last digit, and then it reads the ones in.
Yeah, so the first 1, 2, 3, yeah. At the 4th clock cycle, this one changes to that first bit of 1. But then you have to read the next 3. So it takes 7 cycles total to get the data in and out. Do you guys know what I mean by a cycle?
Clock cycle?
It's what?
Clock cycle?
Correct. So a clock cycle means that it goes up and down. So that's what I mean by a cycle. A full pulse is 1 cycle. Okay, parallel in and serial out. As I go through this, think about how many cycles it's going to take. These all come in at one time, going in. So say I had 1100. So again, the last one will be my most significant bit, 1100. 0011. Okay. So the first cycle, I can read out on the output that 1 at the first cycle. Because it will be sitting before it, then it cycles, and then it changes the flip-flop as it cycles. So first cycle reads everything in, it just takes 1 cycle in. And then how many cycles out? It will be 3 more cycles to get the data out. So this will take a total of 4 cycles. And this was 4 cycles. 1, 2, 3, at the 4th, yeah, 4 cycles. So that one took 4 cycles, that one took 7, this takes 4. On this one, everything goes in. It takes 1 cycle to go into the flip-flop, and then everything can be read. So this just takes 1 cycle, parallel in, parallel out. All right, questions about any of this? Okay. All right, the different types of flip-flops then that are in there. So the D flip-flop The D flip-flop has probably the simplest. It has a clock, a D input, and then it has on the output a Q, and a Q bar. And the Q bar is just literally the opposite of the Q. And so it's one of the simpler ones. So as you clock, whatever is at the D input goes to the output. It does have a reset or clear option. What do you think clear or reset means? Yeah.
Is it set to 0?
Yep. Output goes to 0. So it basically clears it. Yes.
What do you mean when you say clock? Like, I don't get it.
So last time we built that 555 timer, and you saw that it gave you a repetitive signal. So on that, if you hooked up something to like that to this clock wire, it's going to look like that. It will go up and down based on where your high and your low value is for whatever you consider that high and low value. So one cycle of it is when it goes up and then down is considered a cycle. So the clock would be a continuous cycling of these. So you can create, so in lab you're actually going to create a manual clock where you'll push a button and it will go high, and then you'll take it off and it will go low. And so you'll create this cycle manually, but it is the transition from a low state to a high state to a low state. So that is what is meant by a clock, is a low, high, low. Does that help? Clarify? Okay. So low, high, low. So that would be one clock cycle. Okay. Hopefully that makes more sense as far as what I'm talking about with a clock. So clock is a continuous one of these, but it can also just be one pulse of down, up, down. Okay. SR flip-flop. In an SR flip-flop, it's just a little bit more complicated because you have two inputs now instead of just the single input. The issue with this one is that you have a issue when both the S and the R are 1. So this is called an invalid state. And so a lot of times SRs are not used that much. But when you're building them discretely, SRs are a little bit easier to get to work right. The JK flip-flop is like the next complicated one. It's more complex, but it doesn't have that invalid state. So most of the time you're going to be working with a JK flip-flop, and when we look at the counter, it's going to be with a JK flip-flop. And the reason is that it has an extra combination. So when J is basically 0, well, when these are the same, 0, 0, your Q will basically, your output, so this is more your output, and then this is the next output. So if you're, it does determine based on what your previous output was, what the next output was. So maybe I'll call this an input. That might be easier to think about this. So think about this as your output, and this is actually as an input. So this is that previous state It depends on that, unlike what we looked at with the D flip-flop, but it doesn't depend on what that last state was. It just depends on what is coming in the clock. So if you have, go back to that one, if you have 0 coming in, then your output will be 0 out. If your 1 is in, then you get 1 out. And if you're 0, then you'll get 0. If you're 1, and you're 1. So that one is just simpler, where whatever you have on it, it just kind of puts it into that D flip-flop, and your output will be based on that. JK, on the other hand, depends on what your previous state was to what your next state is. So this is current state and next state. So it uses that current state, even though it was your previous output, as basically another input. So in this case, when you have J and K is 0 and you have 0, 1, this basically keeps the data in there the same. So no change. When you have a 1 and a 1, it basically toggles your output. So if your current state's a 0, it goes to a 1. If your current state's a 1, it goes back to 0. So this is called a toggle state. And this is very useful in a counter situation, because if you tie these to 1s, then you don't have to do anything, and it will automatically actually keep counting for you. And you'll see how this can be connected to do that.
For overflow? Or,
Forever. Mm-hmm.
no, for overflow? Like when never mind.
So yeah, I'll show you how you hook it up. Yeah, and it depends on how you want to hook it up. We're going to do an asynchronous one, which doesn't, well, it's kind of confusing because there's a clock in there that gets it going, and then it will continue. All right. So these are going to be, most of the time you're going to use this to either store the data and keep it there constantly. The other one is if J is 0 and then your K is opposite, 1. And then if you have a 0 or if you have a 1, it just sets it basically to a 0. So if your J is 0, it sets to 0. And in this one, if you have a 1 on the J, your K has to be opposite, and then it sets it, no matter what you have, to a 1. So that's basically kind of how the JK will work. Here's a comparison of them. The SR is usually easy to build, and so if you're not using a chip, that's usually the easiest one to build discretely. And so, a lot of people use that just to build it quickly and keep it as a little memory device. But it keeps that invalid state, which can confuse your logic. The D is more like whatever your input is, it then stores that input as the output. And then the JK is a toggle. It has a set and reset on it. Again, reset would be setting the output to 0. It has all valid states, but it's more complex. So counters count in binary. And to count in binary, what do you see as the pattern in this first column? 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay, so it keeps going 0, 1, 0, 1. What about the second one? 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Third column, it goes in 4s. Yep. And then it goes in 8s. Seeing a pattern with this? Okay. Next one would be
16.
every 16. It would go zeros for 16 and then ones for 16. So it will go by 2 raised to the power of whatever that is. Okay, so that's the number of times it will repeat itself. So to make a clock, so this is, if you look at this, you will see like, oh, this is 0, yes, that's binary 0, this is binary 1, 2 raised to the 2, this will be, or 2 raised to the 1 will be 2, then 2 plus 1 is 3, and then 2 raised to the 2 is 4, and then 4 plus 1 is 5, 4 plus 2 is 6, 6 plus 1 will be 7, so it is counting in decimals, etc. Okay? So this is how that binary counter works. So what we want is that we want one flip-flop to just continuously toggle 0, 1, 0, 1. The next one we want it to go for 2 and then toggle and then stay. So toggle, then stay, toggle, then stay. So this is how you would actually create it in JK flip-flops. So you would we're going to put them all in that toggle state. So we're going to tie all the J and Ks to that high value. And then we're going to feed the clock only into the first one. And then this will then be fed as our clock into the second one. Then we'll feed this in as the clock to the third one and the clock to the fourth one. So this is going to be our, it's called most significant bit. MSB. And then this is going to be the one that's going to go, Q0 will be the one that goes every other one. So 0, 1, 0, 1, 0, 1, 0, 1. And it's called the least significant bit. So first one comes in, the clock goes in. And what do we want to do to this, all of these first? I'm going to tie all of this, the reset or clear, and we're going to set it to 0 or 1 based on what that needs. So I'll show you in a second. So we're going to clear it first. So set everything to 0, and then you'll want to start toggling it. So first one, it would go in, it would be 0 first, so what will be Q0? It will go to a 1 because it will have set. So reset, everything will go zeros. And then the first clock cycle comes in here, and this will change to a 1. But when does it change the next one? What has to happen in a cycle? It goes low, high, and low. So then the next one will toggle after that one changes back to a 0, then this one will flip to a 1. Then that goes 1 again, then to 0, and then it will turn it again, which will then change it to a 0, which then will flip this one to a 1. So that's why there's kind of that delay there. It's got to go 0, 1, 0 in order for it to change. Okay, so this was working a second ago. Okay, there it goes. I was like, no, it was right behind it. Okay, get to the right spot. Third one. Okay, so in circuit verse, if you guys that have computers and want to open this up, yes.
So to
So I'll show you. So so this is my clock that I'm using here. And this is a D flip-flop, which you can't really see here. So this one will be, you can see in the corner, it will come up, it says D flip-flop on it. And then your JK flip-flop will be right underneath it. So on the D flip-flop, which is on the top, we had our input, which was just whatever's in, will go out, and then it changes on the clock timing. So if I change it, once the clock goes, then it changes. So you can see that. Okay, so for the JK, I've tied both of the, okay, so this is the set, or in the clear, it's not the set, the clear one. So when I put high, it will clear it, and then it should then change this once I go to 0, it will run. And then watch with the D flip-flop should change to a 1. And then this one is set high, so it should toggle this over to also a 1. So you can see that it does, and then it keeps changing the JK going back and forth based on the timing of the clock. Does that help visualize it? Okay. All right, so you guys are then gonna build, so this was hopefully a good demo of this, and then you're gonna build the JK flip-flops for the counter. I can't remember which one's which now. Okay, so this is the counter. Let's do the shift register first. So use the D flip-flops and do 4 of them. And then put an input and watch as it shifts, and change your input and kind of watch as it shifts the numbers over. And remember that this last one is going to be your most significant, and then this one will be the least significant. All right, so take a minute to create this. And again, if you don't have your computer, meet your neighbor who has it and work with them so that you can see. It's gonna help us. Also, while you guys are doing this, if you want to pull up the quiz for today, there is a quiz for today. And so you're welcome to do it also at the same time.
Okay.
Yeah, oh yeah, yeah. Yeah, that makes sense. Oh, I understand that.
Looking at the grades.
Right here, right here. Oh yeah, I know it should be. I just did that right now.
You don't have to put the ones on the top if you don't want, those are output boxes, but I just thought it was easier to read from left to right instead of right to left. But just, the way that you really want to do is just see that output and this, and output and this.
Oh, it's like this one. Over the year. Yes.
Okay, so say I want to put in like a 1010. I would need to change manually my input at each clock. So I'm going to say, okay, now I'm starting. So I have a 1, now I have a 0, now I have a 1, then I have a 0. So I have to time it with the clock so that it changes before the next clock cycles in. What would I do different to, so this is which type of shift register? Serial in, and I'm reading it as parallel out. If I didn't read it as parallel out up here, I would then have to read it out at this wire. So I would have to read it out here. So if I had 1, 0, 1, 0, and then I'm reading 1, now it changes to the 0, then it changes to the 1, then it changes to the 0, and I'm always reading it at that output wire. That would be serial in, serial out. I would then, instead of shifting it, I would then put them all in as 1 in, and then I would read them out if it's parallel in, serial out. Sorry. And then parallel in, parallel out would just be all in at one time, and then I'd read the outputs all at once. Okay, any questions about this one? Okay. So now move to the JK flip-flops. Oh, and you're going to build that counter. So on this one, there's this asynchronous reset. So you're going to tie that all to the same line, and then when you put that as a 1, it's going to reset all of those flip-flops. So it would start out as all 0, and then I'm going to tie all of my JK inputs to high, and then when I put this at a 0, it should start counting. So because these were backwards, I put them on the top to be the right way. So you're going to see 0, 1, 0, 1. That one's going to keep changing. And it just looked a little bit more confusing having them backwards. So that's why I put them up above. So go ahead and try and build this one, and then watch as it counts. What? Huh?
Is this one right? Oh, it is. Oh, I guess
Is Will Kimball here? Jack Strobe, Ethan Nichols, Brandon Lai, Anashuba, Anubesha, Wyatt, Brady, Malone, Lizette, Perez, Jean Tiang, Pang, who's not here. If you haven't picked up your exam, grab it so I don't have to carry it anymore. I thought I saw him. No. Can I see yours? Oh, sorry. Thanks, I don't want to carry them anymore. Thank you. Okay, so some of the question is, well, what do I need to know for the exam? You might have to build these kind of circuits. So I'm not going to have you build these circuits. So we're going to go over some other problems so that you can kind of know what to expect for the exam. So Unit 3, practice problems are now available. That is going to be a very good location to get ideas of what kind of questions. Yes? Uh-huh. So that's a good question. Like what kind of questions could I ask from here? So if I say in the binary counter you have a 0, 1, 0, 1, what would be the next number? That would be something I could ask. Explain a clock to me. And that would be something I would ask that you would be like, well, it's something that goes low, high, low would be one way of describing it. Or it could be multiple choice answers of kind of what is a clock? What is a cycle? What kind of flip-flop do you want to use for a counter? JK. What kind of flip-flop do you want to use for a shift register? D. Okay, so understanding those. I already asked what is a shift register, asynchronous or synchronous? It's synchronous because it has a clock. Understanding what it means to have serial in, serial out, parallel in, serial out, all four of those. And so being able to describe in words what those mean. Those would be some of the other ones I could ask. Okay, so some other questions. So what does a truth table represent? Okay. All right. So understanding what a truth table is. What is the purpose of a clock in sequential logic circuits? Correct. Okay. Convert the following binary number to a decimal number. So take a second to convert that. Okay. Heard 1990. Heard 90. What others? Okay. So 2 to the 0, 2 to the 1. This would be 2 to the 2, 2 to the 3. This would be 2 to the 4th. What's 2 to the 4th? 16 plus 2 plus 1. It is 19. So being able to convert from binary to decimal and from decimal to binary. So converting 21. So you can do 21 divided by 2 is going to be 10, remainder 1. 10 divided by 2 is 5, remainder 0. 5 divided by 2 is 2, remainder 1. And then 2 divided by 2 is 0, remainder 0. Wait, I missed one. Where did I miss? 10. 10 divided by 2 is 5. 5 divided by 2. One. And then 1 divided by 2 is 0. Remainder 1. I was like, I'm missing something somewhere. Okay, so what's your first number? Well, 1. So the other thing is you could note, oh, it's very big. So it's 16, well, put it through here. So you know you have 16 plus 4 plus 1. So you can also do it that way, is just like, oh, okay, well, the division of those, I know I have at least 16, and then I have to add more on. What kind of truth table is this? For what gate? NAND gate, correct. Whoever said that, great job. And this is a truth table for what kind of gate? Somebody said that very quickly. XOR, correct. So remember, for the XOR, it's a 1 when they're opposite, and then a 0 when they're the same. So it's that one. All right, so this one, I could give you a truth table and say, create the logic for X. So with this, you would then say, okay, I need to understand that I need to do a sum of products for this one. So writing or I could ask you for the Boolean expression of it. So this would be X is A bar, B bar, C, or A bar, B, C. And the circuit would then be 2 AND gates and an OR gate. And the inputs would be A bar, B bar, C, A bar, B, C. So I could ask you to, draw the circuit for it. And it could be any function. This one asked what single gate in block D will create the function for y. So what would this need to be? It has input of B and C bar. So looking at B and C bar, is this and another one, this one. And then y is a 1, 1, 1, and 1. So when you have C bar, so I'll draw it next to it. So what gate would be there? So it'd really be this one. So I had somebody say XOR. So one way you could do this is rule out some of them. So you see here you have a 0 and a 1, and then your output is a 1. So that gives you the possibilities of which gates? Or an XOR. So then you would go to the next one and you say, oh, it's a 0, 0, 0, so that still matches both. A 1, 0, an OR gate would be a 1 out, but this one has a 0 out. Or wait, sorry, I missed the wrong one. 1, 1, and an OR would be a 1 out, but this has a 0 out. So it rules out the OR gate. So you could say it could have been an OR gate, but it's not an OR gate. So then you just check the rest and make sure it fits. So 1, 0 is a 1, a 0, 1, 1, 0, 0, 0, 0, or 1, 1, 0, and then 1, 0, 1. So yes, it meets the XOR function. So this is another type of problem that I could ask for. Go down. So this is an XOR. All right, filling in this truth table. So here's a given combinational circuit, and you would need to fill in the values. So this one doesn't give me a temporary output here, so I'm going to call it C. And I'm going to create another column for C. So the XOR of A and B would be 0, 1, 1, and 0. And then my output X is going to take that C and B, and it's another XOR. So 0, 0 would be 0, 1, 1 would be 0, 0, 1 would be 1, and 1, 0 would be 1. And then I take the NAND output of X and B again. So this one this time and B. And that would give me a NAND of 0, 0 is going to be what? 1. And 1, 0 will be 1. 1, 0, 1 will be 1. And then 1, 1, 0. So those would be my outputs. Okay, so you could expect also a combinational logic and then have to fill in the truth table for it. And then for the auto correct, I may ask you to sum up the column of X's and what would be your value there. Something like that to do a check. But we will again grade based on what you put on your paper. Okay, a user button press from a remote is correct, asynchronous to the system clock. What is the main difference between asynchronous and synchronous sequential logic? Heard somebody say the first one. Are there any others? Is this true? Synchronous logic does not use a clock signal. That one's incorrect, right? Synchronous logic uses a clock signal. So uses. Asynchronous logic depends on a clock signal. So does not. Synchronous logic changes state immediately with input changes. Changes state immediately with clock. Okay. In a common cathode 7-segment display, driving segment A high will, correct, turn signal A on. Okay, so this is kind of the questions you could expect kind of for that 7-segment, is understanding like on was 1 and the high is 1.
Turn it off or on?
What? Oh, yep, sorry, I missed. Turn it on, yes, turn A on if it's high. The low is when it turns it off. I just mismarked that. A register stores multiple bits by so that we made the shift register. How did we make it? Correct. We grouped flip-flops in parallel. Or we just grouped flip-flops together. Okay. So that's your takeaway from that. What kind of flip-flop? D flip-flop. Is particularly the one we did. All right. What did the capacitor do in a 555 timer circuit? Correct. It controlled the timing of the frequency. Oh, that's a typo. Or the length. It's supposed to be or the length of time of that one pulse. So remember, you'd had either one. One was the frequency of how fast it was switching, and then the other one was how long it went. Okay, a 4-bit register can store. I heard somebody say the last one, correct. It can store up to the number 15, right? Because it has a bit for each one. So it had 1, 2, 3, 4. This would be 2, 0, 2, 1, 2, 2, 2, 3, 8, 4, 2, 1. So that's 15. So a state diagram helps you. Correct, visualize, allow transitions. What is the output of the finite, so FSM, finite state machine, when the correct sequence is completed? Correct, the output went to a 1. Otherwise, it was always 0. What does SIPO stand for? Correct. What does PISO stand for? Correct. All right. Kind of as I said, being able to create the combinational logic for any of those 3 outputs. Understand what does a clock cycle mean, kind of how many clock cycles for each configuration below, which is what we went through. What's this first one? Correct, serial in, parallel out. What's this one? Correct, serial in, serial out. This one? Parallel in, serial out, and this last one. Okay. So hopefully this gives you a better feeling of what to expect for the exam and what you kind of need to study and prepare for. All right. See you guys on Wednesday.